So let's do one more quick equilibrium example. So I've got, this is actually the reverse of a reaction that we've been playing around with here, but we've got phosphorus trichloride now reacting with chlorine, molecular chlorine, to give us PCl5. So the setup is we have a 5-liter box, it's 25 degrees Celsius. We have 0.05 moles of PCl3, 0.02 moles of Cl2, and 0.2 moles of PCl5. So mind the zeros. And the goal now is to figure out if this is an equilibrated mixture. And we know that the Kc at this temperature is 1000. Again, first thing to note though, moles. And these things are not in terms of concentrations. I mean, they're in terms of concentrations, not amounts. So the first thing we need to do is to convert them into concentrations. You've got the amount. I gave you the volume. So we've got 0.01 molar PCl3. We have 0.004 molar PCl2 and 0.04 molar PCl5. Again, mind the zeros. And plug and chug here, so the equilibrium constant expression, don't forget, products over reactants, raised to the appropriate power. So we've got the concentration of PCl5 to the first power, divided by the concentration of PCl3 to the first power, and then divided by the concentration of Cl2 to the first power. Plug in the numbers, and that gives us a value of 1000 here, which means that this mixture is equilibrated. Now, let's tinker with the system a little bit. We're going to add another spike of PCl3. I'm going to call it 0.06 moles. Which means that the PCl3 concentration at that instant is going to be 0.022 molar. And the other concentrations at that instant haven't changed. We have 0.04 molar chlorine and 0.04 molar phosphorus pentachloride. Now you can probably figure out what happened here is we actually disturbed this equilibrium. So let's see what happens to that same concentration expression that we used for the equilibrium constant calculation. And if you plug in these new numbers, and again, it's the PCl3 concentration that has changed here, so now this one is different. And now, and because, well, this number is different, the end result is different. Now, which means that since it is not equal to 1000, that the system is not at equilibrium. And we sort of knew that because, well, we just up and added something to a system that was already at equilibrium. So by definition, we were disturbing that equilibrium. So this tells us that it's not equilibrated, which means it is reacting. And the question is, which way is it reacting? And the answer can be told here with this number. All right, so fresh slide here, but same information. So this reaction was going to proceed until that expression equals 1000 again. And this is why, notice again, this is not equilibrated. So this is, I didn't use Kc anymore. This is this thing called Q. Now it's going to, that factor, or that quotient, is going to, the reaction is going to react spontaneously in the direction that makes that reaction approach 1000, or that value approach 1000, and then stop. So how do we need to do that? Well, that number needs to get larger because 1000 is larger than 454, which means that we need to increase the numerator and decrease the denominator. Remember that by the nature of what this expression is, these two don't happen separately. If you increase the concentration of, the products, the reactants, the reactant concentrations have to go down and vice versa. So we want to increase the numerator. The numerator is the concentration of the products. The denominator is the concentration of the reactants. We want to increase the product concentrations, decrease the reactant concentrations, and that's kind of what we call reacting in the forward direction. So you've seen it. We're going to formally define it here. There's this new thing called a reaction quotient Q. Now these things are, this is a value that is constructed exactly the same way that the equilibrium constants K are, except that they are any instantaneous set of concentrations, not necessarily those of an equilibrium mixture. So then again, they're constructed the same way. So for a generic reaction, AA plus BB giving you CC plus DD, it is, I apologize for the order here, but it's constructed in exactly the same way. That you've got the concentrations of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. And so it turns out that these are a very common general thing, and that the equilibrium constants are actually subsets of reaction quotients where the concentrations are specifically those of an equilibrium mixture. And for the reaction quotient Q, that is any reaction composition. So we talked about this thing getting back to equilibrium. Let's get some more ice table practice and see how that would work. All right, so let's get this going here. So for the initial conditions, again, that are not equilibrated, I just got the concentrations that I calculated after that addition of the extra PCl3. And just because it's not on here, this is PCl3. Here's the Cl2. And here's the PCl5. Now, so we had an inkling that because we added PCl3, and we calculated our reaction quotient, and we determined that the reaction is going to be reacting spontaneously in the forward direction. So that means we can expect a loss of some amount of the PCl3. By extension, we're going to lose some of the Cl2 with it, and you're going to increase the amount of PCl5. Remember, we said we were going to increase the denominator, that's this concentration, and increase the numerator, which is this concentration, and decrease the denominator, which is these concentrations. And algebraically, our equilibrium concentrations are going to be these symbolic amounts. This is also going to be, or would be, very good quadratic equation practice for you. So I would encourage you to do this. The quadratic equation that you need to end up solving will be this one right here. And the roots will be these two right here. And the question is, which one is reasonable and which one isn't? Now you will note that in this case, they are both positive. So you can't just use the, the negative one is going to be the impossible or the unreasonable root, and you shouldn't do that anyway. So you need to look at the sizes here. And this one right here, the 0.02507, if you look, will give you a negative concentration of PCl5. It will give you a negative concentration of Cl2 for that matter, and the only positive concentration you'll get is for PCl5. I'm sorry, it will give you a negative concentration for PCl3, which means that that root is the unreasonable one. And this is the one that you want to use. And you can double check, but this one will return positive concentrations for each component here. And if you do that, you get these new concentrations right here. So again, we've dropped a little bit of PCl3, we've dropped a little bit of Cl2, picked up a little bit of PCl5. Now, and this should be an equilibrated mixture. And if you want to check yourself and your quadratic equation math, just plug them back in to the equilibrium constant expression. And if you do it with these new numbers here, you should get 1,000, or 1,000 within rounding error, which means, hey, we're good. All right, now, did we go back to exactly the same place that we were before we added the PCl3? And this is a subtle point. So this system did go back to equilibrium, but did it end up in exactly the same place? And if you compare those sets of concentrations, the answer is no, it actually didn't. And you need to be, aware of this. So when an equilibrium system is disturbed, the system reacts in a way to counteract the disturbance that was made and go back to some equilibrium composition. But it's not the same thing as completely negating the change. The reason why this is the case is, if you think about it, we only added PCl3, right? And if we didn't add Cl2 with it, because they have to react together, the ratio of their concentrations actually is going to end up different, even though the entire reaction quotient is the same. So you counteract to minimize the disturbance, but generally you never completely negate it, as shown by the fact that these two concentrations are, sets of concentrations aren't the same.